All right, so we have seen confusion and diffusion, but the question is, how can I create a confusion and diffusion, right? So in block cipher design, there are two famous methods, but actually there are popular three methods. They are substitution permutation networks, SPNs, Feistel networks, but which became recently popular is sponge functions or permutation-based cryptography. So you can create block ciphers from sponge functions. So I will try to give a picture for all of them. But the main idea is that instead of designing a very complex algorithm as a cipher, design something simple which we call round, which provides both confusion and diffusion, then repeat that process many times so that it will be easier to analyze. That is the main idea behind block cipher design. Okay. So we will use a secret key, but we want to use the secret key information in each round. So you can use that key directly there for somehow, but you can also use an algorithm called key schedule, which actually takes input as your secret key and provides round keys, which we will be using in each round. Okay. So instead of using the key directly in every round, a key schedule algorithm is used to generate round keys from the secret key. So first start with SPN, substitution permutation network. So in SPNs, we have three layers. Key addition, this combines your round key with your plaintext or the input. Substitution provides confusion, and permutation layer provides diffusion. So of course, sometimes you can take the key addition from here and here. It depends on how you actually define it. Famous block ciphers like AES or present, which is an IOS standard, are examples for SPN, which we will see next week in detail. But I will briefly mention present because it is very easy to understand because it's a lightweight design. So here is a general picture I drew for SPN. So you have a key, you put it in the key schedule, and it provides round keys. Okay, you use these round keys at the round key addition layer. So you have the input, you combine with your round key, then you perform substitution, permutation, and key addition layers, substitution, permutation, key addition. So this is your actual single round. Okay, this is another round. So if you have 10 rounds, then you repeat this process 10 times. So now you might think why we are doing this. Okay, assume that we always assume that the person who's eavesdropping always captures the ciphertext, right? So think about the single block. So I have a plain text block. I encrypt it with the secret key and obtain the ciphertext block, and I transfer it to internet or something. So you captured the ciphertext. You know the algorithm details, but knowing the ciphertext doesn't allow you to capture any key materials, or it doesn't allow you to go backwards to obtain the plaintext, because in the first step, you don't know the round key, so you cannot go to the intermediate layers. Similarly, even if you know what the plaintext is and the corresponding ciphertext is, it doesn't give you any idea about the intermediate steps. So I'm actually masking my steps using the add round key layer here, and you don't know that secret information. That is the main idea. Okay. So let's look at a very concrete example. This is present. It is an IOS standard for lightweight cryptography. So this is a single round of present. So this simple picture actually shows you the cipher design. Okay. So it has a block size of 64 bits, and each line here actually represents single bit. So there are 64 lines at the top. Key length depends on the user. You can choose 80 or 120, but I insist that 80 bit is not secure nowadays. You should choose 128 bits. And this cipher consists of 31 rounds. This means that you take this picture, copy it to the bottom of it, again and again 31 times. So at the end, you will end up with these lines. So there's a key addition layer at the end. Okay, this is how we design the cipher. So let's look at how the plaintext is encrypted. So you have a plaintext block, 64 bits here. So you XOR it with your round key. So regardless of how many bits your master secret key is. From the key schedule, 64 bits of round keys come here. So you simply XOR them. So it is an addition modulo 2. Okay, we talked about XOR before. So this single line actually is your key addition layer here. Okay. So these S boxes is your confusion layer. So as you can see, there is a box here. It takes 4-bit input and provides 4-bit output, right? So assume that all of your input bits are 0. In hexadecimal, it means 0. The S box definition says that replace it with C. C, again, if you turn it into integers, it's 12. But if you represent it in bits, it becomes 1, 1, 0, 0. Most of the time, the rightmost bit is considered as the least significant bit, but you have to define it when you're doing this kind of operations, okay? But during this course, most of the time, the rightmost bit will be the least significant one. If you use it as the most significant one, then C becomes 0, 0, 1, 1. So this is why it is important. You have to know your representation. So it actually replaces 4-bit input with some other 4-bit. So this is where you create confusion. Okay, most of the time security comes from the confusion layer, but it only confuses these 4 bits. So if you don't perform this permutation layer, Cipher modifying this bit does not affect the other S box. So for this reason, you change the places of the bits, so you actually permute them. But the idea is as follows. For instance, in the S0, this bit stays at the same place. So in the following round, it will come here and again be the input of S0, the rightmost S box. But this bit goes to, I think, the 16 bit. So in the next one, it goes to S4. This bit goes to S8 here, and this one goes to S12. So this choice of permutation actually allows you a good diffusion. So it is as simple as that. So this is a block cipher. You can just go home and implement it and use it. As simple as that. Of course, I didn't only mention the key schedule, but from your master key, you just rotate and perform a few operations and obtain the round keys, which we'll see in the next week. Okay. I'm showing this picture because it is easier to understand, and many of the block ciphers, if you go back, for a single block, this is how we encrypt it. Okay. So in the decryption part, you have to go backwards. So every operation should have an inverse in this SPN ciphers. Okay. So if we move on to the second design, it is called Feistel network. It was introduced by Horst Feistel. In the Feistel network, a round function consists of a round function and the swap operation. Idea is as follows. You divide your b-bit input into 2 parts. Round function is applied to one half, then XOR to the other half. You use the key material inside this round function. Then you swap these 2 parts. So let's look at the picture. You have a plain text block here. For instance, if it is 64 bits, this line will represent 32 bits, and this line will represent 32 bits. So from the key schedule, you again obtain round keys. But this right part goes into the round function. In the round function, you have key addition, confusion, and diffusion layers. And the result is XORed here. So this part is modified, left part, but right part is not modified, right? It stays the same. So in the next round, right part becomes left, and left part becomes the right. And it goes this way. But of course, you can complicate things. For instance, Cipher, again, it is an IOC standard for lightweight crypto. Instead of 2 parts, you have 4 parts here. So we call it a generalized Feistel. You can even have 8 and so on. The third part, generally, most people don't know it because they use lecture materials from 30 years ago. So nobody knows sponge constructions nowadays. But it is the most famous part in the symmetric crypto these days. I give an example with an ASCON, authenticated encryption algorithm. So it works like this. In the middle, you have a permutation, and there it is a huge state, like 320 bits, but it can be 1000, like in the check and so on. Okay, but you have 320 bits, and you fill it with IV, which is fixed, your 128-bit secret key, and 64-bit nonce. Okay, so you fill a huge internal state. Then you perform confusion and diffusion on this input. And the output, once you have the plain text, for instance, 64 bits, you XOR it with the top part of this internal state, and you provide the result at the 64-bit ciphertext. Recall that your internal state is huge, but you only use small part of it to encrypt the plain text block. Then you perform permutation again on the internal state, so you again create confusion and diffusion and provide output again and again and again. Okay, so this is a very strange design compared to others. But as you can see, there is a letter R and C. R represents your rate. So in ASCON, it is 64 bits, so you actually encrypt in 64 bits at every permutation. And C is your capacity. If it is larger, then you feel more secure because you have a huge internal state which is secret, and you use only a small rate of it to encrypt it. So we will talk about this in the following weeks. I will show you how to implement ASCON in C so that you can implement other ciphers when you do your homework again in C. Okay. Very strange design, but we call it a sponge function because it has an internal state. So think it as if it's a sponge which you fill with water. You squeeze it, and some part of it, the water goes outside. That is why they call it a sponge construction. So Feistel and SPN are used for a very long time. They have some pros and cons. In the Feistel, encryption algorithm is identical to the decryption algorithm. Only the order of the round keys change. This is important. So if we go back to picture, once we encrypt, as you can see, the arrows goes this way. So you perform the round function in this part, and provide output. Once you have the ciphertext and once you have to decrypt, you don't have to go to the round function from the opposite side because you know this part. You put it here, move it here, XOR it here, and obtain this part. So you don't have the inverse of operations in the Feistel ciphers. But in the SPN, in order to go from here to here, so you have to use the inverse permutation. Here you have to use inverse substitution. So this provides a bonus. But for the SPN, we have the bonus of having that a single run affects the whole input, which is a nice thing. And the cons are the exact opposites. In the Feistel, a single run only affects half of the input. And for the SPN, decryption procedure requires the inverse of the substitution and permutation layers. This might be, for the computer, might not be a problem. But if you're doing it on the hardware, this means that you have to use more space for these operations, right? So let's look at design considerations for different platforms, and let's compare hardware versus software. Hardware implementations can easily work on bits. Since most programming languages in software focus on bytes, bit operations are more costly on software. Just think about the design of present. We were permuting the bits. Doing it using a programming language takes a lot of time. But in the hardware, you just say that this bit goes to this bit, and that's it. Cipher design also determines the number of gates required to perform encryption on hardware. So number of gates determine the area required. So if you need a lightweight design, then you have to choose your operations in a very nice way. That is the idea. And we also have small devices like microprocessors and so on. So code size or required memory is not a big problem for software implementations due to fast CPUs and large RAMs. But if you want to work on very smaller microcontrollers, then your code size, required memory, etc., affects the performance on those devices. Another thing we consider is the security versus speed. So speed is generally measured as throughput, so gigabits per second or megabits per second, etc. Adding more security measures, for instance, increasing the number of runs, increases security, but now you have to perform more operations, so this reduces the speed. So you have to find a sweet spot which gives you the best security and best performance. Ciphers performing well on hardware or software may not be suitable for constrained devices like RFID systems or sensor networks due to limited memory battery or computational power. Hence, we also need lightweight ciphers. This is why I actually teach another course about lightweight cryptography. Okay. So let me finish with this slide. So at the NIST side, we have some standards, but AES is actually currently the only standard. NIST supports triple DES, performing the DES operation 3 times consecutively. But the thing is that they will remove it after 2024. They announced it like this. So after that, triple DES will not be a NIST standard. They have script check, which is designed by NSA, and it has 80-bit secret key, so it is not secure, but it is in the standards for legacy use. So at the NIST side, there is only one standard, we can say, and that is AES, Advanced Encryption Standard. At the ISO's part, we have more standards. AES also here, but we have a lot of block ciphers as the standards, but height was broken. In my master's thesis, I actually broke almost a full height. In the lightweight side, we had Present and Calafia in 2012, but a few years ago, I think in 2019, they also added LIA as a lightweight block cipher. So we have 3 standards for lightweight block ciphers, and I think 7 block ciphers, which are ISO standards. But everybody is using AES anyway, so having those other standards are not that important. And since these are not patented, you can freely use them. You don't have to do anything, or you don't need to take any permission. So this is the good thing about ciphers. You can freely use them.